In my video on convolution, I explained how a digital image can be considered to be a general function represented by a sequence of numbers. In my first Fourier video, I explained that the input to a discrete Fourier transform, or DFT, is just a sequence of values, but with the caveat that each value is actually a pair of numbers, like a coordinate point. I mentioned that the output of the DFT is also a list of pairs of numbers called the Fourier coefficients. However, the Fourier transform represents the input signal as a series of harmonic waves over a range of frequencies, and these harmonics add up to make the original input signal. So how exactly do those Fourier coefficients, those pairs of numbers, relate to these harmonic waves? That's what I'll be talking about today. If you've only ever seen simple accounts of the Fourier transform, you might be forgiven for thinking that the outputs of a Fourier transform are a set of sinusoid harmonics, one harmonic per frequency in the signal, and if they mention Fourier coefficients, you might have been led to believe that those coefficients are numbers describing the amplitude of those harmonic waves, as depicted in this graphic here. However, these notions are too simplistic, and you'll need a more detailed knowledge to work with Fourier transforms in practice. So, in this section, I'll give you the big picture overview of what the DFT actually outputs, and in the next section, I'll go into specifics. So, what the DFT actually outputs is a pair of numbers per frequency. These two numbers are called the Fourier coefficients for that frequency, and each pair constitutes a single complex number. So, one number is the real component, and the other one is the imaginary component. See my first Fourier video if you need a quick refresher about complex and imaginary numbers. These two coefficients are used by the inverse DFT in two different ways to define two separate harmonics. However, this is only half the story. As I explained in my second Fourier video, each absolute frequency comes in two forms, which we can describe as the positive form and the negative form. There are two special exceptions to this, but for most frequencies this is the case. So, for each absolute frequency, the DFT actually defines four harmonics. When performing the inverse transform to sum up the harmonics to reproduce the spatial domain signal, one pair of these harmonics takes part in the summation that produces the real component of that spatial domain signal, and the other pair take part in the sum that produces the imaginary component of that signal. So, in the end, you actually get two harmonics per absolute frequency for reconstructing the real component of the input signal, and two more harmonics per the same absolute frequency for reconstructing the imaginary component of the input signal. But why does the DFT need to create four harmonics per absolute frequency? Wouldn't it be more efficient to just define two, one to recreate the real component of the input signal and one to recreate the imaginary component? And why do it in this seemingly overcomplicated way, with all this recombination activity? Well, this is what I'll explain in the rest of this video. So, that was the big picture. Now let's examine some specifics. For example, how do you specify some general harmonic wave using only two coefficient numbers? I'll explain this by making an analogy with how we specify some general vector on the Cartesian real plane. So let's say we need some way to specify any length line pointing in any direction and originating at the center of the plane. In other words, a general vector with its origin at 0, 0. Clearly, there are an infinite number of such possible vectors when you consider that the length can be any value at all in a continuous range from 0 to infinity, and likewise the angles can be any number in a continuous range from 0 to 2 pi. So, the set of all eligible vectors contains an infinite number of members. Our goal is to find a way to specify any single specific vector from this infinite set using only two coefficient numbers. Well, you already know the solution to this. We simply select two vectors from the set to act as index vectors. Then we can use two coefficients to multiply those two vectors, and the resultant of those coefficient-scaled index vectors can define any specific vector in the set. What are the properties of these index vectors that make them suitable to use for this purpose? For maximum information efficiency, we want the vectors to convey positioning information that is independent of each other, in the sense that a change in one of them will not cause our resultant vector to change in the direction of the other one. This means that the two index vectors must be at 90 degrees to each other, or orthogonal as mathematicians call it. See my first Fourier video for an introduction to orthogonality. Also, it helps to simplify the calculation of our coefficients if the index vectors are centered at the origin point directly along the x and y axes, both point in the positive direction of their axes, and finally, each has a magnitude of 1. This last criterion is called normalization of the vectors, and when two orthogonal vectors are normalized like this, mathematicians call them orthonormal vectors, and not just orthogonal. So now we have a set of only two orthonormal index vectors that can be used as a basis to identify any one of an infinite set of general vectors using just two coefficients. Our set of two orthonormal vectors are therefore described as being a set of basis vectors for that reason. So, just as we can define a set of orthonormal basis vectors to efficiently identify any one of an infinite set of vectors, so likewise we can define a set of two orthonormal basis functions to allow us to identify any one of an infinite set of functions. For example, consider as our set of functions the set of all possible sinusoid waves with the same frequency. Even though we've restricted the set to allow sinusoids of only one frequency, such a set contains an infinite number of members, because the amplitude of the sinusoids can vary continuously from 0 to infinity, and furthermore, each one of these waves can exist at any one of a continuous range of phase angles, that is, the angle representing the starting point in the up-down cycle of the wave. Although phase angle has a limited range of 0 to 2 pi, that range is continuous, so there are an infinite number of possible phase angles to choose from. So this set of functions contains an infinite number of members. Now, just as we could define two orthonormal basis vectors to define any one of our infinite set of vectors, so in this case we can select two sinusoid functions from our infinite set to act as a pair of orthonormal basis functions, which, when we multiply each one by a coefficient and combine them, can allow us to define any one of this infinite set of sinusoid functions. Those two orthonormal basis functions are the pure sine function and pure cosine function, each normalized to have an amplitude of 1. With this spreadsheet, I'll demonstrate how this works. I can adjust the frequency of the waves with this variable, but for this demo I'll stick to a frequency of 2 for clarity, and to begin with I'll use a positive frequency. On the left there's the unit sine function, and below that the unit cosine function. I'm going to multiply or scale each of these unit functions with a coefficient that I'm calling alpha for the sine function and beta for the cosine. So alpha and beta play the role of the two Fourier coefficients in a DFT. Up the top here I plot the current values of alpha and beta so you can see how they relate to each other. Currently you can see that they are equal to each other, each with a value of 0.5. In the middle here we have the scaled versions of the sine and cosine basis functions. And on the right is the resultant function, that is, the sinusoid that results from adding the scaled sine and cosine basis functions together. In this demo, I've arranged it such that alpha and beta always sum to 1. So when alpha is increased, the value of beta is proportionately decreased, and vice versa. This is not a fundamental restriction or condition of Fourier coefficients in general, it's just a condition I've arbitrarily imposed for the purpose of the first part of this demo. Clearly, when alpha is 1, it means that the sum contains only sine wave and no cosine component, so the phase of the resulting sum is the same as the phase of a pure sine wave. Let's define this as a phase angle of 0. As we gradually decrease the alpha coefficient and increase beta, the proportion of cosine wave in the mix increases, and the resultant wave gradually shifts in phase until, when alpha is 0 and beta is 1, only the cosine component contributes to the sum, so the phase shift of the resultant wave is pi over 2, compared to what we started with. I know that the amplitude also changes over this range, but ignore that for now. I'll show you how to control the amplitude with the same two coefficients later. The point I'm trying to make now is that by specifying the correct proportion of the coefficients of a sine and cosine basis function, we can specify with just these two coefficients a sinusoidal wave with any phase we like, but so far only in the range between 0 and π/2. That is, we can only start our compound wave anywhere in the first quarter of a full sine wave cycle. However, a general signal may contain harmonic waves of any phase at all, so how can we extend this range? Well, one easy way to get more phase range is to just repeat this range but use negative coefficients instead of positive ones. This effectively gives us the ability to make a wave with any phase in the third quarter of the cycle, as shown. But how can we make resultant waves with phases in the second and last quarters of the cycle? Those of you who watched my previous Fourier video will know where I'm going with this. So far, we've done as much as we can with basis functions that look like this, and they allow us to make harmonics with any phase in the first and third quarters of a cycle. To generate harmonics with the remaining phases, we need to use another pair of basis functions, a pair that look like this. As I showed in my previous video, we could generate this pair using positive frequencies and an inverted sine function. However, it's mathematically simpler to use the same sine and cosine basis functions, but just flip the sign of the frequency variable within them. So we use a negative version of the same frequency we had before. This generates the required new basis wave shapes without the need to alter the actual basis functions. If you don't understand this, take a look at my second Fourier video for an explanation. So, using various proportions of these negative frequency basis functions and positive coefficients, we can vary the coefficient proportions to give us a resultant wave that covers the second quarter of the cycle, from π/2 to π. And by using negative coefficients together with this negative frequency, we can get the waves that start in the last quarter of the cycle, so they have a phase anywhere between 3π/2 and 2π. So, by using the standard sine and cosine as orthonormal basis functions, together with some combination of positive and negative versions of the same absolute frequency value, and positive and negative coefficients, we can generate, with only two coefficients, a resultant wave that can have any phase at all throughout the entire 2π range. So now you know how only two coefficients allow the DFT to describe a general harmonic wave with any possible phase for a given absolute frequency. The next question is, how do we represent these waves at any possible amplitude? Well, the answer is very simple. We simply scale those two coefficients in size without altering their relative proportions. The bigger we make them, the greater the amplitude of the resultant wave, and the smaller we make them, the smaller the amplitude of the resultant wave. And, as we've seen previously, we can make the coefficients negative to represent a negative amplitude. As long as we scale the two coefficients together in such a way as to preserve their relative sizes, the phase of the resultant wave will not be altered, only its amplitude. So, with only two numbers, we can specify any waveform of any amplitude and any phase, but only at one absolute frequency. This is why the DFT outputs two coefficients per frequency. Now, that explains how two Fourier coefficients can specify one general harmonic wave. But I said earlier that these two Fourier coefficients actually specify two harmonics, one that takes part in reconstructing the real part of the signal, and the other that takes part in synthesizing the imaginary part of the signal. So how can only two Fourier coefficients specify two potentially different harmonic waves? The answer is also very simple. The DFT uses the same two coefficients, but it uses them in two different ways to make two harmonics with them. First, it uses the two coefficients to multiply cos and sine basis functions, and the two scaled component waves are then added together to give one harmonic wave, the wave that takes part in the summation that produces the real component of the input signal. And in the second case, the same two Fourier coefficients are used to multiply sine and cos, so the other way round. And not only that, but this time the component waves are subtracted from each other to produce the second harmonic, the one that takes part in the summation that produces the imaginary component of the input signal. This double harmonic generation happens for each frequency, both positive and negative. So that's how we get 4 harmonics per absolute frequency, with the exception of the zero order and the absolute Nyquist. This, together with the odd and even symmetries of the sine and cosine basis functions, is an indication of the mechanism underlying the special symmetries inherent in the Fourier transform, which I'll describe in more detail in the next section of this video. Finally, as you've been watching all this, another question might have popped into your mind. If the positive frequencies are needed to specify a harmonic with a phase from one half of the phase range, and the negative frequencies are needed to specify a harmonic with a phase from the other half of the phase range, why does the DFT generate two coefficients for both positive and negative versions of the same basic frequency, thereby generating harmonic waves from both? Surely it only needs to generate a harmonic from either the positive or the negative version of the frequency for that harmonic to have a phase from anywhere in the whole phase range. So why is it wasting its time generating both positive and negative frequency coefficients? In other words, 4 coefficients at every absolute frequency. Well, the answer is that it needs to mix harmonics from both positive and negative versions of the same frequency so it can perform a dual parallel solving action. That is, so it can reconstruct both the real and imaginary components of its input signal when these can vary independently from each other. This answer might not make sense to you right now, but by the end of the next section, it will. So, now that you understand the basic principles behind the DFT in some detail, let's try and reinforce that theory by playing with some actual DFT calculations on a small signal. To that end, I've made some spreadsheets where I've calculated some Fourier transforms. I'll leave a link to these spreadsheets in the video description below if you want to play with them to get an intuitive feel for how the Fourier transform works. This spreadsheet implements the DFT for a complex input signal consisting in 5 data points, so k goes from 0 to 4. This page shows the input signal we're going to transform. These are the real components, and this is a plot of them, and these are the imaginary components of the input signal, which are plotted on this chart here. I've arranged the real components into the shape of a ramp. For now, I've set all the imaginary components to 0, so our input signal is purely real. Also, this input function has no symmetries, either even or odd. Note that the lines between the points are not part of the signal. I only put them in to make it easier to see the basic shape of the function. Here you can see the output of the Fourier transform, that is, the Fourier coefficients, which this spreadsheet calculates in real time. So as soon as I change the input function values, the Fourier coefficients get updated, as well as all the graphs I'll show you shortly. So these are the real components of the Fourier coefficients for each of these frequencies, calculated using this formula. And these are the imaginary components for those Fourier coefficients, calculated using this formula. These Fourier coefficients are plotted on this chart here, and you can clearly see some symmetries in the result, with the real coefficients showing even symmetry about the 0-order frequency, and the imaginary coefficients showing odd symmetry. This will always be the case, no matter how many data points the input function has, provided the input function is a non-symmetric and purely real function, and so has all its imaginary components set to 0. This particular combination of even and odd symmetries in the Fourier coefficients is an example of what mathematicians call Hermitian symmetry. But why do we get this Hermitian symmetry in this case? First, note that the even symmetry shown for the real coefficients is the same type of symmetry shown by any pure cosine function. Also, this odd symmetry displayed by the imaginary Fourier coefficients is the same kind of symmetry shown by any pure sine function. Is that a coincidence? No. The reason for this is clear if you recall from my first Fourier video that, in this special case where all the imaginary components of the input function are 0, the forward DFT formulae simplify down to these equations, whereby the real Fourier coefficients are calculated entirely from cosine functions, and the imaginary coefficients are calculated entirely from sine functions. Thus, the Fourier coefficients of a strictly real and non-symmetric input function have no choice but to display Hermitian symmetry. Now let's move on to this sheet, which shows the inverse transform. First note that the recovered values are exactly equal to the input values for both real and imaginary components of the input signal. On the right are graphical representations of the harmonics defined by the Fourier coefficients for each frequency. On the top here are the harmonics used in the summation term of the inverse transform to reconstruct the real components of the input signal, and on the bottom are the harmonics used to reconstruct the imaginary components of the input signal. Recall that the DFT only calculates the values of these sinusoids at the sample points shown by the marker labels. But I've calculated the other values of the sinusoids in between so you can see their sinusoidal shape more clearly. This shaded region here is the flyback period. In this example, it's the interval between k equals 4, which is the 5th sample point, and k equals 5, which would represent the 6th sample point if we had more samples. This area is that part of the sinusoid wave cycle where the sinusoid returns back to start a new repeat cycle. So the amplitude value at k equals 5 is the same as the amplitude value at k equals 0. This feature, where the waveform repeats itself when copies of it are stacked next to each other, is true for all waveforms in the DFT at all frequencies, because the DFT only uses whole numbers of wave cycles in all its waveforms. I discussed these concepts of cyclicity and discrete frequencies in more detail in my second Fourier video. Let's examine the imaginary component harmonics first. You can see that there are 4 of them. 1 for frequency +1, this red line here, 1 for frequency -1, this yellow line, and 1 each for plus and minus frequency 2. I'm not plotting the zero-order harmonic because that's just a flat line, and for the imaginary components you can see from the Fourier coefficient values here that the zero order will be a flat line at level 0, so just overlapping the horizontal axis. Immediately you can see that the symmetries are such that the positive frequency version of each harmonic is exactly equal in amplitude and opposite in sign to the negative frequency version of that harmonic. So all 4 harmonics are symmetrically distributed about 0, and it's obvious that the result of summing up these harmonics will be 0 at all points, hence the result here. This is a direct result of the even and odd symmetries of the Fourier coefficients, because in the inverse DFT for the imaginary component of the reconstructed signal, the even symmetric real coefficients are multiplying sine waves, which by their nature have odd symmetry. This combination, therefore, preserves the odd symmetry in the resulting harmonics. Also, the odd symmetric imaginary Fourier coefficients are used to multiply cosine functions, and so they impose their odd symmetry on the resulting harmonics. So that's why all harmonics used in reconstructing the imaginary components of the input signal end up with odd symmetry and cancel each other out to 0. Now, look at the harmonics for the real component of the reconstructed signal. At first sight, you might think that there are only 2 harmonics here, but no, there are still 4. It's just that the Fourier coefficient symmetries in this part of the equations are arranged such as to force the positive and negative frequency versions of a particular harmonic to be exactly equal to each other. They are duplicate pairs, instead of being equal and opposite pairs as for the imaginary harmonics. Notice also that the values are not symmetrically distributed about the 0 line. These central values are all at 0, but on this side they are more negative than positive, and on this side the reverse is true, so you can already make out that it is plausible that these will add up to our original ramp function. Before I move on, I want to pause here and remind you of something I showed you in my first Fourier video. Recall from when I did this Fourier synthesis practical demo, I only appeared to use half the number of harmonics compared to the full set I showed you later on in this diagram. However, that full set consists in duplicate pairs of harmonics. So, before printing, I simply added the duplicate pairs together to give half as many harmonics, but with each compound harmonic having twice the contrast of its twin components. Well, now you should be able to understand why those duplicates existed, in the case of the input function being non-symmetric and purely real, that is, with all the imaginary components set to 0. Okay. Now let's continue with analyzing the harmonics in our spreadsheet. To see what's going on with the harmonics a bit more clearly, I made these 2 sheets. Each one shows the positive and negative frequency harmonics for a single absolute frequency value. So this sheet shows the positive and negative frequency harmonics for the lower frequency. On the left are the harmonics used in reconstructing the real component of the input signal, and on the right are the harmonics for the imaginary component. You can see that the real harmonics are identical to each other, such that when you add them together, you get this compound harmonic, which is the same shape as each of the positive and negative frequency harmonics, but just twice the amplitude. Most basic level Fourier demos only show you these compound harmonics without telling you that they are compound and without explaining where they come from. Over here, the imaginary harmonics are equal but opposite to each other, so add up to 0. and this sheet shows the same data but for the higher frequency harmonics. Finally, I made this sheet which shows you the waveform you get when you sum up all the harmonics, including the DC zero-order component, and divide by the scaling constant of the inverse DFT. So this is the full inverse transform plot. Remember, only the values at the original sample positions of the input function are calculated by the DFT. And you can see that at those positions we have exactly 5, 4, 3, 2, and 1, a precise reproduction of the input signal, and all the corresponding imaginary values are 0. Again, this shaded area shows the flyback segment before the signal repeats over and over due to the periodic repetitive cyclic nature of the harmonics that make it up. Note that the gradient of the signal at this point must be equal to the gradient at the beginning, because this is a continuous transition, since it is formed by the summation of cyclic periodic sinusoidal waveforms. So, that was the situation and the symmetries seen with a purely real and non-symmetric input function. Now I'll add a non-zero imaginary component to the input function to make it proper complex. The imaginary component can be completely independent in shape to the real component. So, in a way, the DFT performs two transforms in parallel at the same time. In this example, I'll make the imaginary component a step function, like this, so it is also non-symmetric. I'll keep the real component exactly as it was before. The first thing you notice is that we've lost the Hermitian symmetry in the Fourier coefficients, so let's see what this does to the harmonics. You'll note that the inverse transform reconstructs both real and imaginary components perfectly, as expected. Because the imaginary components are no longer 0, we've lost the perfect balanced symmetry of their 4 harmonics about the 0 line. And if you step back a bit, you might be able to convince yourself that the imbalance really is of a type that might sum up to a kind of step function. However, perhaps even more interesting is to see what's happened to the real component harmonics. Now all 4 harmonics are clearly different to each other. They are no longer duplicate pairs as before. But they still add up to the exact same function we had before. So what's going on? Well, you see, this is why the DFT uses both positive and negative versions of each frequency instead of just one or the other, as I discussed at the end of the previous section. Using 2 harmonics for each frequency, positive and negative, gives the DFT the freedom it needs to make the same compound harmonic result for each frequency using different component harmonics. It's like in plain arithmetic. If you have a goal of making a specific number, let's say the number 8, if you're only allowed to make this result with one variable, a, then you have no choice, no freedom. A must be equal to 8. However, if you're allowed to use 2 variables, a plus b, then you have an unlimited freedom of choice. You could use 0 plus 8, or 1 plus 7, or 2 plus 6, or minus 4 plus 12, whatever. If we now go over to the lower frequency harmonics page, note how for the real harmonics, the positive and negative frequency harmonics have shifted in relative phase and amplitude compared to the previous situation we examined where we had a completely real signal. But also note that when you add these 2 harmonics together, you get exactly the same compound harmonic for the real component as in the previous example, using the purely real signal. So, the mathematical logic of the forward DFT automatically chooses the values of the real and imaginary Fourier coefficients such that, when used via the inverse DFT in a way to make the harmonics for the real component of the signal, gives the correct compound harmonic to recreate the real part of the signal, while at the same time, when those same coefficients are used to make the harmonics for the imaginary component of the signal, they give the correct compound harmonic to recreate the imaginary part of the signal, even though these 2 parts of the signal may be completely uncorrelated with each other. It is this super efficient parallel processing simultaneous equation type genius of the DFT that you simply can't appreciate from those introductory basic videos that don't make a distinction between positive and negative frequencies and only show you the end result compound harmonics for a purely real function. So finally, here are the full summation plots showing how the real component is reconstructed just as before, but now we also have a perfect reconstruction of our non-zero imaginary step function component. Although this waveform doesn't look like the step function we started with, remember that the DFT only uses the values at the sample positions. So if you look there, you'll see it forms 1, 1, 2, 3, 3, exactly as the input signal dictated. Now let me go back to my little image example and show you this effect on the DFT there. So this time, instead of using a purely real input image, I'll use a proper complex input with the imaginary component in the form of a letter X. If we look at the positive and negative frequency harmonics for the real component in this DFT and compare them to those we had when the input was purely real, you can see that we no longer have the matching equal harmonics for the positive and negative versions of each frequency as we had before. However, if we add the positive and negative frequency harmonics together for any single absolute frequency, the resulting compound harmonic is exactly the same in both situations. So if I made compound harmonics for each absolute frequency, I'll end up with the exact same set of compound harmonics I used before. The more you play with these spreadsheets, the more of an intuitive feel you'll get for the various symmetries involved in the Fourier transform. A list of the various symmetries is shown in this table. So far, I've only shown you examples for cases where the input signals themselves have no symmetries. If you'd like to explore the other entries in this table with my spreadsheets using various types of symmetrical input functions, note that you need to take account of the fact that I started the index at 0 for my input signals instead of having index 0 in the middle of the function. See the note at the bottom of this slide for some example symmetric input signals you can try. In summary, this video explained the importance of the use of both positive and negative frequency basis functions in the DFT, how this enables the DFT to define harmonics with any phase at all, and also how this enables two completely different signals to be reconstructed simultaneously. I also discussed the various symmetries seen in the Fourier coefficients and how Hermitian symmetry of the Fourier coefficients can be explained by the way the DFT forms these coefficients for a purely real and non-symmetric signal. You can also see from the table that anti-Hermitian symmetry exists in the case where the input signal is purely imaginary and non-symmetric. And even though I haven't explained it in this video, you should be able to work out why. By now, if you've been following my videos, you should have a detailed understanding of the DFT for any one-dimensional signal, and you should also have some idea of how these look for 2D image signals from the few examples I showed you along the way. In my next video, I'll discuss the DFT for two-dimensional signals, in other words for images, in more detail, and I'll go over some examples of Fourier-based image processing. If you like this video, please hit the thumbs up like button and view some of the other videos on my channel. If you'd like to support the project, you can do that by subscribing to this channel and telling others about it. If you'd like to help me continue this work, take a look at my Patreon page, where you'll find additional content and early bird access to future videos. Thanks for watching.